Good afternoon, everybody. Today is the last lecture in the course on thermodynamics, lecture number 7, and it would be about third law of thermodynamics. As any other law in physics, it would be difficult to prove this law mathematically. Physical laws are derived from experience. It is something that we observe in our everyday experience. Then third law of thermodynamics is a little special because it is a law about very low temperatures. So we don't do experiments at very low temperatures every day. That's why understanding this law created quite some problems. And this is why discovery of this law occurred only at the beginning of 20th century, when people eventually realized how to achieve very low temperatures. How did they come to this law? Well, normally in thermodynamics, when we were talking about entropy, we were talking about difference in entropy, and we were not interested in absolute value of entropy. The very same story was also valid for the case of Gibbs function, for instance. We were mainly interested in the difference of Gibbs functions, or in the fact that the difference is negative, because this is the law, that the processes that spontaneously evolve in nature can only evolve spontaneously if the difference in specific Gibbs function or in Gibbs function is negative, and the system always tries to reach the minimum of this Gibbs function. So once again, we were interested in the difference and not in absolute value. But the last lecture, we introduced chemical potential, which, as we showed during the last lecture, is Gibbs function of a single particle. And at that moment, when we were talking about physics of chemical reactions, it became obvious that we would like to know the absolute value of chemical potential, because absolute value of chemical potential is important for calculation of equilibrium constant, evenwichtconstante. That's why, after the development of physics of chemical reaction and after formulation of law of mass action, people came with the next question about absolute value of chemical potential. How can we find it? And it was Nernst who was thinking about chemical potential, and he realized that in order to know absolute value of chemical potential, we must know absolute value of entropy, and this is exactly what we haven't discussed yet. And he started to think about behavior of entropy upon approaching very low temperatures. And let's look together at the problem. Imagine that I take a little bit of heat from system at certain temperature T, then entropy decreases. Then I decrease temperature more, and I take the very same amount of heat from the system, and entropy decreases even more. Then I go to even lower temperatures, give the same amount of heat from the system, and then we have already huge decrease of entropy, because temperature gets lower and lower, and taking the very same amount of heat from the system leads to the increasingly high change of entropy. Eventually, if you approach 0, if you simply follow this expression, approaching 0 should lead to infinitely large decrease of entropy if you take a little amount of heat from the system. It is sort of paradox. Something interesting should happen at 0 Kelvin. So Nernst was following logic like this. So let's think in terms of thermodynamic potential, which is called enthalpy, and which is defined like this. This is internal energy, this is pressure, this is volume. And in terms of Gibbs function, I will remind you, Gibbs function is a thermodynamic potential which is defined by an expression like this. Obviously, if you calculate the difference, you will see that the difference is equal to T times S, temperature times entropy. And if you look at the behavior of this difference upon approaching 0 Kelvin, obviously it will approach 0 because temperature goes to 0, assuming that entropy, of course, stays, doesn't go to infinity, so it doesn't diverge. Then the next step, what we can make is to look at the differentials of enthalpy and differential of Gibbs function. The very same expressions we can rewrite in terms of change. So substituting d on delta. Then we'll look at the difference again between difference in enthalpy and difference in Gibbs function. And if you assume that you are talking about isothermal process during which temperature doesn't change, then again this difference should be 0. So what we have here, we have two expressions. One says if we approach 0 Kelvin, the difference between enthalpy and Gibbs function disappears, and another says that the difference in enthalpy upon changing certain parameter, I don't know which parameter, but upon changing certain parameter, and the difference in Gibbs function upon changing the very same parameter will also disappear if we approach 0 Kelvin. Then, for clarity, they stated here that we are talking about processes during which temperature is constant. Well, looking at this behavior, then Nernst proposed that enthalpy in Gibbs function should behave something like this. So enthalpy in Gibbs function upon approaching 0 Kelvin should reach the very same value as we saw, but also they should start changing similarly. So they change equivalently. And Nernst came with the hypothesis an expression like this should be valid. Basically, the very same statement that upon approaching 0 Kelvin, enthalpy and Gibbs function behave equivalently. There is no rule for these statements. It is just it was derived based on intuition, based on and also analysis of experimental data, and based on the general considerations. So he started with this statement. Then he wrote an expression for the change in entropy applied hospital rule to this equation, and what he observed what he obtained is expression like this, where, as we can see, this part should be equal to 0. So it means that the whole expression is equal to 0. From where we derive that approaching 0 Kelvin, if we are talking about isothermal process, entropy stop changing. So basically it means that approaching absolute zero, entropy of some substances approach a well-defined constant. So it doesn't diverge as we proposed at the very beginning of the lecture, as we anticipated at the very beginning of the lecture, but upon approaching 0 Kelvin, entropy becomes a well-defined constant. So here you can see a quote from original book published by Ernst, where he says that a long study of relation between enthalpy and Gibbs function in the past years has led me, so basically him, to the hypothesis that we are dealing with a law, a more or less appropriate at ordinary temperatures, but true at the neighborhood of absolute zero. And he proposed that the entropy of a system at absolute zero is a well-defined constant. Once again, the thing that we have shown here. As I said, as any other law in physics, this law is difficult to prove mathematically, but there are many other observations showing that this law is true. One of the consequences of this law for entropy at very low temperature is the statement that absolute zero can never be achieved. The law of unattainability of absolute zero. It is impossible to reduce temperature of any system or a part of a system to the absolute zero in a finite number of operations. In order to demonstrate this law of unattainability of absolute zero, we can follow first graphical approach, where this is entropy, this is temperature, and imagine that entropy depends on temperature and also on some quantity x. If we assume that at absolute zero entropy is not well-defined constant, then we can expect two dependencies for entropy as a function of temperature, one for quantity x equal to x1 and another one for quantity x equal to x2. Then imagine we are sitting somewhere here, the temperature of the system is somewhere here, and we would like to cool system down. and a number of operations. There are two things to remember. First of all, the most efficient process of cooling down is adiabatic cooling down. So the most efficient process of cooling down is a process during which entropy doesn't change. So it means that we will cool down in a step like this. And what we also have to remember, that upon temperature increase, entropy can only increase. Well, it's more or less obvious statement, because if you look at the heat capacity defined at parameter x constant and defined for the case when we change temperature, heat capacity is positive, and it means that this expression should be positive as well. It basically shows that if you decrease temperature, entropy will decrease. If you increase temperature, entropy will increase. So we try to cool system down, and then it means that you can do this in a number of steps, and one of the steps should be adiabatic cooling down. So we go from from the state with x equal to x2 to state with x equal to x1. Then there must be process that decreases entropy. And again, we go in adiabatic way and eventually arrive to absolute zero. So it basically shows that if you postulate that at 0 Kelvin entropy is not a well-defined constant, then it means that you can achieve the absolute zero. But situation is totally different if you postulate that at low temperature, at 0 Kelvin, entropy must be a well-defined constant. Then if you try to repeat the very same steps, you will go in steps like this. And here, upon approaching this region, when two entropies are already very close to each other, you will have difficulties to make this step to lower value of entropy, and it means that if you want to reach absolute zero, it will require infinite number of steps. So already from these two pictures you can see that absolute zero is unattainable if we assume that entropy is a well-defined constant at absolute zero. The very same thing can be shown mathematically. So as I said, we assume that entropy is a function of temperature and some parameter x. Entropy then can be found as integration constants, or in fact entropy at 0 temperature plus an integral from 0 to T1 and entropy at temperature T2 and x2 is equal to integration constants entropy is 0 Kelvin. Adiabatic cooling means entropy doesn't change. Third law of thermodynamics says at absolute zero, entropy is a well-defined constant. Then it means that from all these expressions, we can state that these two integrals must be mutually equal. And if you assume that T2 is equal to 0, they can be equal only if T1 is equal to 0. Which basically says that there is no adiabatic path from T not equal to 0, from temperature to which is not equal to 0, to a state with temperature equal to 0. So you can arrive to this point of absolute 0 if you're already at absolute 0. If you're not, there is no adiabatic path that will bring you to this point. So this basically shows that if you assume that at 0 Kelvin entropy is well-defined constant, absolute 0 cannot be achieved. Well, as I said, maybe it is not the best experimental proof of the third law of thermodynamics. So that if you cannot achieve something, it's difficult to prove that it is absolutely impossible. That's why even Nernst tried to come up with a proof of third law of thermodynamics, and one of his proposals for such a proof was proposal based on Carnot cycle. So he tried to show that third law of thermodynamics can in principle be proven based on first law of thermodynamics and second law of thermodynamics. And he said, let's imagine a Carnot cycle that operates between two reservoirs, temperature T1, temperature T2, and we assume that the cold reservoir is at absolute 0. Then it means here it should accept some heat, here it will reject some heat, there will be some work performed. In accordance with the definition of the efficiency of the of a heat engine, we expect an expression like this, and since this is Carnot cycle, it will be also equal to 1 minus ratio of temperatures of the cold and the hot reservoir. And if we assume that T2 is equal to 0, it would mean that Q2 should be equal to 0, and if this Q2 is equal to 0, then the efficiency is equal to 1, and the whole heat transformed to the working body will be transformed into work, which contradicts the second law of thermodynamics. Fine. However, Nernst was soon criticized that although the proof is fully correct, if you assume that cold reservoir at the absolute 0, it will immediately give you a situation that contradicts the second law of thermodynamics. However, it doesn't prove that absolute 0 cannot be achieved. It only proves that a Carnot cycle will not operate if the temperature of one of the reservoirs is 0. Let's talk about other consequences of the third law of thermodynamics. Well, if you assume that at 0 Kelvin entropy is well-defined constant, so it means approaching very low temperatures entropy doesn't change, then it would also mean that at absolute 0 all the processes are isothermal and adiabatic at the same time. Then we will show with the next slides that approaching absolute 0, many response functions like isobaric cubic expansivity, compressibility, heat capacity, so all these response functions experience anomalies. And maybe the most interesting anomaly to start with is anomaly of heat capacity at absolute 0. So the very first lecture we defined heat capacity with an expression like this, and entropy, in accordance with the definition of entropy, is given by this expression, where, of course, we should talk only about reversible processes if we talk about definition of entropy. So as you can see, heat capacity is a function of entropy. Already from here, you can anticipate that if entropy experiences anomalies at very low temperatures, also some anomalies should be expected for the heat capacity. So I like the following reasoning that allows us to show that upon approaching 0 Kelvin, heat capacity should approach 0 as well. For this, I will use this definition expression for entropy in terms of difference of enthalpy and Gibbs function. Then I will again apply hospital rule but to this expression. Then we discuss processes when only heat is transferred to the system, no work is performed. So it means that this expression should be valid. And according to the definition of heat capacity, this derivative is basically equal to the heat capacity. And according to the definition of Gibbs function, this derivative is equal to minus entropy. So it means that the expression between parentheses here is heat capacity plus entropy. And since we know that approaching 0 temperatures, it should be 0, and entropy is also here, should be 0, it will immediately give you this was for B. Yes, it will immediately give you that heat capacity will tend to 0 as well. So here, as a quantity x, I basically assumed that this is pressure. So here, from here on, we consider the case when the pressure is fixed. So it means that here we consider heat capacity at constant pressure while temperature is changing. And the very same expression you can find for every other heat capacity, just keeping choosing another constant here. It is a general behavior, it is a general rule that upon approaching 0 Kelvin, heat capacity tends to 0. As I said, many other response functions experience anomalies upon approaching absolute 0. We can review derivations which we did before. For instance, at lecture 3, we derived Maxwell relation for surface tension, where you showed that if you look at temperature derivative of surface tension, it is equal to minus 1 over temperature, and then derivative of heat with respect to surface area of the liquid under consideration here. And this derivative should be taken at constant temperature. And you can see that if entropy is constant at 0 temperature, so it means that the derivative of entropy with respect to surface area at constant temperature should be equal to 0 as well. And it means that surface tension or the temperature derivative of surface tension must be equal to 0 as well. So it means that if the temperature tends to 0, surface tension becomes a constant. Here you may ask me, who will be interested in surface tension of liquids under such a low temperatures? And apparently this question indeed intrigued people long ago, almost 100 years ago, when Kimel and Onnes generated liquid helium, and apparently he was one of the first who was able to achieve very low temperatures. They realized the fact that liquids at the very low temperatures should behave differently, they should show anomalies, and they measured surface tension of liquid helium, and they indeed found anomaly. While surface tension was increasing linearly upon the temperature increase, while reaching temperature of 2 Kelvin, they saw a saturation, the anomaly that they expected. Anomaly that one would expect based on third law of thermodynamics and Maxwell relations. So another anomaly that we can reveal, it's just one of the anomalies, it's not necessarily, it's the main one, just an example. Is a so-called isobaric cubic expansivity, a quantity that characterizes how volume of medium changes upon temperature. Expansivity. So if you look at this derivative, then for this derivative you can derive Maxwell relation according to the third law of thermodynamics. At very low temperatures, entropy is a well-defined constant, so it means that if you change whatever quantity, being at temperatures very close to absolute zero, entropy doesn't change. And if this is the case, it also means this quantity tends to zero, from where we conclude that expansivity when approaching absolute zero tends to zero as well. Another example is compressibility. Which is defined like this. It's a derivative of volume with respect to pressure. And this derivative of volume with respect to pressure you can express differently using reciprocity theorem. And since we showed previously that upon approaching zero, this derivative tends to zero, it would also mean that this derivative will tend to zero as well, from where we conclude that also compressibility upon approaching absolute zero tends to zero. So as I said, response functions upon approaching absolute zero experience anomalies, and this you can see in all these examples, including heat capacity. Few more examples I would like to give. So one of the examples is related to magnetism at very low temperatures. At the second lecture, we derived a law for temperature dependence of magnetization in a ferromagnetic material. And this temperature dependence of magnetization in a ferromagnetic material basically showed that the magnetization is proportional to the square root of the difference between critical temperature and temperature of the magnet. Third law of thermodynamics introduces correction to this law, and it says that this law is valid, but only at high temperatures, but at low temperatures, we should take into account third law of thermodynamics, which says that entropy change is equal to 0. So, in order to apply third law of thermodynamics, I derive Maxwell relation, but for the case of magnetic medium, since at low temperatures entropy is well-defined constant, it means that this derivative at absolute 0 should be equal to 0, from where it follows that this derivative should be equal to 0 as well. Which actually means that third law of thermodynamics forbids any non-zero slope here. So third law of thermodynamics says that magnetization should behave in this way as a function of temperature. I also copied for you several papers showing that indeed anomalies of response functions upon approaching very low temperatures can be seen experimentally. This is related to anomaly of a behavior of paramagnetic susceptibility. This graph shows you that there is indeed anomaly in heat capacity, which tends to grow first upon decrease of temperature, but while you cross temperature of 1 Kelvin, heat capacity goes to zero quantities, zero values. Also, in the case of phase transitions, in particular in the case of phase transitions superconductors, we can derive Maxwell relations and show that there must be some laws applied in relation to behavior of critical field, for instance, as a function of temperature, field that destroys superconductivity. All these features show, all these things show that upon approaching absolute zero, you do have anomalies which once again and again show that third law of thermodynamics actually works. As any other law of physics, there are plenty of experimental evidences that it simply works. As a take-home message today, I hope I was able to convince you that third law of thermodynamics is a very fundamental law. It states that as the temperature of system approaches absolute zero, entropy approaches a well-defined constant. Thermodynamics itself doesn't specify how large the entropy at absolute zero is. But approaching absolute zero, many response functions also approach zero, and this can be proven, or experience anomalies like the entropy becomes zero. And from third law of thermodynamics, it follows that absolute zero is unattainable. So it's impossible to reach 0 Kelvin. To complete the course, let me show you one more example that emphasizes that knowing thermodynamics, you can apply it practically in every area of physics and learn more about physics in general. And I would like to give you an example from electromagnetism. Consider you have a case when you apply electric field to a medium. This electric field in general induces polarization. Normally, in the textbooks of first year of the university education, it is assumed that vectors of electric field and polarization are parallel. In principle, it is not always true, and then a lot of complications in physics emerge when we take realistic media into account, where in principle electric field and the polarization induced by this electric field could be vectors pointing in different directions. So as I said, electric field would be the vector, polarization would be vector, and according to properties of media, these vectors are not parallel. So these kind of media are called anisotropic media. In this case, this susceptibility chi, which was formerly a scalar, becomes a matrix. What can we say about this matrix? Well, first of all, let's write this algebra a little bit differently. Where chi will be matrix with two coefficients, and I is a coefficient for vector p, showing the coordinate of vector p, and j is a coefficient showing the coordinate of vector e. Can we say anything about this matrix? And in particular, if you're talking, for instance, in the given coordinate system, if you're talking about two elements, xy and yx, what is the relation between them? Thermodynamics can help you to figure out these questions. In order to understand these questions, we start with first law of thermodynamics, where Q is equal to temperature times differential of entropy. We assume that we consider only reversible processes, so it means that entropy doesn't change. Since we are talking about the case when electric field is applied to a medium and it induces polarization in the medium, then work performed on the system must be written in this way: electric field times differential of polarization. If you ask me why, it's because polarization was defined like this. It was defined as a quantity such that a product of polarization and electric field gives you the energy of interaction of electric field with the medium. And it means that the work performed on the system can be written in a little bit lengthy but a clear form. So here I've taken into account the fact that polarization is a product of matrix and a vector. I basically put this expression to here, assuming linear dependence between polarization and electric field. Then you can integrate, and after integration you will get that the total energy is equal to P, electric field times polarization, and then you will get the expression for the work performed on the medium by the electric field. Now, since we are talking about reversible processes, this is also expression for internal energy. But internal energy is exact differential. So it means I can calculate second derivative while differentiating first with respect to Ej and then with respect to Ei, or calculate second derivative after changing the order of differentiation, and if this equality is valid, it basically says that for this matrix, this expression should be valid. So knowing nothing about electromagnetism, or practically nothing about electromagnetism of the medium which we are talking about, we have been able to find a general law for this coefficient chi, for this matrix chi, which is called electric susceptibility. So this is just one of the simplest examples showing that knowing thermodynamics, you can become very powerful in many other areas of physics and electromagnetism in particular. And while I started the course with the quote of Einstein, who claimed that thermodynamics is probably the most powerful part of physics and universal science that can be applied to many areas of physics, I would like to sum up the course, to conclude the course with a quote of Arnold Sommerfeld, who was a professor of many Nobel Prize winners, who said that thermodynamics is a funny subject. The first time you go through it, you don't understand it at all. The second time you go through it, you think you understand it except 1 or 2 points. The third time you go through it, you know you don't understand it, but by that time you are so used to the subject that it doesn't bother you anymore. So with this quote, I would like to encourage you, keep learning thermodynamics, keep trying to understand thermodynamics better, look for new examples when thermodynamics can be applied and help you to understand physics better in general. And with this, I would like to conclude the course. I would like to wish you good luck with the exam, and of course, Merry Christmas and a very happy New Year 2021. Thank you very much.